Hello everybody and welcome to this week's Hubble Hangout. My name is Tony Darnell. I work at the Space Telescope Science Institute, and once again we've got a great hangout planned for you. Turns out, and I didn't actually know this, but turns out there's water on Ganymede. So it is, and today we've got some observations from a Hubble Space Telescope that were announced earlier today. We've got the scientists on hand who took them to tell us what they found. But before we get started and get going in earnest with the hangout, let me just say a couple of things about Hubble 25 and some things I want to put on your radar. This weekend, we're going to be at South by Southwest. NASA will be at South by Southwest doing all kinds of fun activities. And so if you're in the Austin area, please stop by the booth at the interactive exhibit. And there'll be some panels going on there as well, one on Sunday and another one on Tuesday, the following. So if you follow us on Twitter, and if you aren't, you should be, at Hubble Telescope. You will find out all about that as the weekend progresses. Also, if you're not subscribed to our YouTube channel, which is Hubble Site Channel on YouTube, you need to get that way because we got all kinds of fun things going on that channel as well as Hubble 25th goes on. Also, Hubble Mania is still happening. So if you go to hubble25th.org/go/Hubble-mania, you can vote for your favorite Hubble images, and the link to all that is down in the description box below. Also going on and ending today is the Ode to Hubble video contest, which we're going to talk about a little bit more in just a minute. But first, we want your questions and your comments. So, Scott, why don't you tell everybody how they might be able to do that?
Absolutely. So the easiest way for us to see your questions and comments is to use the Q&A app, which is here on both YouTube and Google+. So whether you're watching it embedded somewhere on another website or on Google+ watching us there, on the very bottom, it will allow you to pop open and ask us a question. I'm already seeing one coming through from W. Vanderheide, and telling us good evening, Hubblers. So that is a great way for us to interact with you. We can actually select your questions and answer them on air, and it puts a timestamp onto when we answer it. You can leave us questions and comments just in the regular YouTube comment area, and also over on Twitter. We are, or I am more, looking over at the hashtag Hubble Hangout, to where we will not only be monitoring questions, but I will be live tweeting and putting out some of the images that we're discussing today during the show. So please feel free to get a hold of us in all those different ways. And as Tony said, subscribe and follow us on Twitter so we can have more of a conversation during and after the show.
Good. Thank you very much, Scott. So we're doing that now. We're Hubblers now, not Hubble Huggers.
I enjoy Hubblers much.
Is that a contraction?
I like Hubblers more than Hubble Hugger. You know me.
Yeah, I don't know. I kind of like Hubble Hugger. But all right, well, take a vote. Tell us what you think. If you want Hubblers, then that's what you are. If you consider yourself a Hubble Hugger, say that too. And I want to know because I kind of like Hubble Hugger better. Okay,
I'll create a poll later on
yeah, good idea. Let's get social.
Right.
You're driving the internet, so that's a good idea. That's a good thing to do. So with that in mind, Hubblers and Hubble Huggers, you love the Hubble Space Telescope, and if you love it enough, you may have felt compelled to make a video and to enter it in a contest to win some really cool prizes. And so if you do plan to enter, today's it. This is your last chance. It ends midnight Central European time, which is about 7 p.m. our time, Eastern time. So you don't have it's just hours left to submit. So please go ahead and do it. And then what happens, and the link to that is in the description box also below. But what happens next is a segment that I'm going to let Georgia Bladen talk about. She's the Hubble manager, the social media person at the European Space Agency, and she has joined us to talk a little more about what's next for the Hubble, the Ode to Hubble video contest. Georgia?
Thanks, Tony. So first of all, a huge thank you to everyone who has sent in their videos. I've had a little sneak peek at the ones we've had so far, and there's some great stuff in there. So, as Tony said, you've got till midnight Central European time tonight to get your entries in if you haven't already. When we've got all of those entries in, at 2 p.m. Central European tomorrow, which I think is 9 a.m. Eastern, you will have the opportunity to crowd vote the entries to get us down to a short list of 6 for each of the 2 categories.
So the URL that you currently have for submitting will change into something else.
Yes, you will see if you go to that page, there'll be 2 links that appear magically tomorrow that you can follow to go and vote for your entries, and the current submission links will take you to the voting pages.
And you have
Yes, I have a little preview that I can show you on what it will look like.
This is what you can expect.
So, when I've got my head around doing this.
Okay. So, so the same URL will be valid tomorrow. You go there, instead of being able to submit, you'll be able to do some voting. While she's getting that up, I'll just tell you they've really got some great things. They've got 2 categories. One of them is for people 25 and under. You're the Hubble generation. And then there's there's another category for people who are over 25, which I just barely missed the window. I used to be I was almost there where I could have been the Hubble generation, but I just missed it.
Yeah, a couple decades, man.
Yeah, sure, Tony. Just by many years.
Yeah. Well, I'm a Hubble old generation, I guess. Okay, go ahead, Georgia. We see your screen.
You're more of an Edwin Hubble generation.
Edwin Hubble. Oh, where's my ball?
Oh, mean.
Harsh. That's really harsh. So this is the page that you will need to go to, that you've got a link to. So this is where the links will appear tomorrow. These links up here, which are currently to submit, you will then be able to use in order to vote. And when you do come to vote, can you see this page?
Yes.
Yeah.
We still see the Ode to Hubble page.
We see the main Ode to Hubble page.
If you've moved,
okay.
That's still what we're seeing.
Pause for suspense. This is my first hangout.
There you go. Okay.
There we are. When you get to this page, this is where you will be able to vote. So you'll have to sign into Facebook. It will take you to a page like this. And all of the videos for that category will then be displayed. Got a sneak peek here. You can play them. You can visit them on YouTube. And to vote, you like them as you would on Facebook. And the 6 for each category that get the most likes will then be sent to our judging panel.
Can you only like
2 winners?
Can you only like one?
No, you can like as many as you like. So if you watch something and you don't like it, don't like it. And if you do like it, then you can like all the ones that you think deserve to be in the shortlist.
All right. So if you don't have a Facebook account, you guys need to get one of those too, because we're going to need you to vote. So, and then the ones that have the most likes. How long will this be going on, Georgia? Oh, it says right there, 1st of April, 2015.
It does indeed. So it'll be until the 1st of April, and then it will go to our panel of judges, and they will select 2 final winners, 1 from each category. And those final winners will be announced at the anniversary on the 24th of April.
Wonderful. And what do they win? This is my favorite part.
What is a great prize, I think. I would say
Me
that.
too, me too.
It's a piece of mounted solar array, ESA made, that was on Hubble. So
an actual piece of an actual solar array that was actually on Hubble.
Actually on Hubble.
Yeah, you actually get your own little bit of Hubble.
Actually
Hubble.
Yes. Well, that's important.
It is. And you also actually get a mounted image of the 25th anniversary image.
Okay, so this solar panel you're talking about, this is the one that was replaced after one of the earlier servicing missions, right?
Yes, indeed.
Cool.
And I believe it spent 6 years in space. So.
Yeah. Okay. So there you go, folks. So are the submissions going along pretty nicely so far?
Yes, it's really good. As I said, we've got a really fantastic range of innovative ideas for the videos, which is what we were wanting. So people have really gone out there and done some really cool stuff. So thank you to all of you who have
I'll be voting too.
To do that.
I'll be voting too. So thank you, Georgia, very much for letting everybody know. You have until midnight Central European time tonight to submit your videos. It's just a few hours away, about 7 o'clock Eastern time. So get your vote or get your submissions in if you haven't yet. You're definitely putting it close here if you don't hurry up. And then we invite you to vote early and vote often on the contest. So thank you, Georgia, for letting everybody know. I will keep you guys posted on the progress of how things going and remind you of it. We're also, and I don't know if I can make this happen or not because they've already left for South by Southwest, but we're going to try to have some QR codes out there that if you are at South by Southwest, you can click on that and participate in the voting that way. So that'll be another way to get involved. So today's hangout, Carol. Hi.
Hey.
Carol
Hello.
Christian, the Hubble Space Telescope Outreach Project scientist. And we got new lower thirds, everybody, courtesy of Scott Lewis. Thank you, Scott.
No problem.
Thank you, Scott.
So anyway, welcome back, Carol. It's good to see you again. She joins me every week. Water on Ganymede. This is big news to me. I didn't know this was even something that could be a thing until
You
today.
are off in the Hubble Deep Field. It has been known for a while.
I know. I am not. The solar system. The solar system does not interest me. I'm sorry. It's just not as interesting. I am not a planetary guy.
I'm going to JPL next week. I'll make sure to let them.
Exactly.
They don't want to hear that at all. Okay, so so joining me are the scientists who were involved in today's press release. We have Dr. Joachim Sauer and as well as Daryl Strobel. They're two of the scientists. Joachim was the principal investigator. Welcome, guys. Also with me is Kurt Rutherford and Lorenz Roth, both of whom participated in part of the team. So welcome, everybody. Let's start with Joachim. What? I read in the press release, and I didn't even know this, but I guess they've hypothesized or predicted or something that there was water on Ganymede?
Yes, speculations and models going back to the 1970s suggest that there could be liquid water under the icy crust of Ganymede. But,
okay, now, go ahead.
Yeah, but the observational evidence for that is very poor. There's only one set of observations by the Galileo orbiter, which flew by like 6 times close at Ganymede and measured the magnetic field there. And they picked up some signal which could be consistent with an ocean, but there was also an alternative explanation. And so we were following up on that question and used the Hubble Space Telescope to look, found a new approach to look with the telescope inside of the moon and confirmed the ocean.
Okay, now this is one of those observations where I always call them, inferred discoveries. It's a lot like dark matter. We know it's there because we can't see it directly, but we can see the effects it has on something we can see, in this case light rays. So we know that if we look at a galaxy and it's lensed in a certain way, you add up all the material that you can see, it doesn't match. There must be something more there that causes the light to bend. So we call whatever that is dark matter. They don't say what it is. They just know something is there, causing the light to bend in a way that would be more than the stuff they can see. So this is one of those kinds of observations, correct? You looked at the magnetic field behavior and then inferred from that behavior the existence of something else, right?
Exactly.
You want to describe that a little bit for us?
And with the telescope, we cannot even directly see the magnetic field. We can see the aurora of Ganymede with the telescope with HST. And Ganymede has 2 auroral belts similar to the Earth. And because Ganymede is also under the influence of Jupiter, so Jupiter's magnetic field changes like with the 10-hour period at the location of Ganymede. So it would make the aurora rock back and forth by 6 degrees. But
so please remind some of us what aurora are. I mean, there may be some people who are aware of aurora, but they may not understand what it is that makes an aurora. Obviously, magnetic field.
Aurora is a light phenomena, like which you can also see here on Earth. Like if you go to Alaska, you look up at the night sky, and then you often can see, like in green or in red colors, light emission. That's it's generated by electrified gas. So if electrons hit the upper atmosphere of the Earth, like this emission is excited. And Ganymede has a thin oxygen atmosphere, and so the oxygen molecules and atoms are excited. They emit light, and if you could stand on Ganymede and look into the night sky, you would see a red aurora in the night sky. You would see it fainter with the naked eye, but you probably could even see it like just standing there. And this is what we observe with Hubble, like these auroral belts around the North Pole and around the South Pole of Ganymede.
So we have an illustration that kind of outlines a schematic of some of that. If you can pull that up for us, Scott, I'd be appreciative. So the aurora are caused by the excitement of these charged particles, which are interacting with the magnetic field. You know what's amazed me, Carol, is that when I was working in solar physics, we were trying to measure the sun's magnetic field, and there were no there's no way to do that directly, is there? There's no way to just measure a magnetic field.
Right. You can't see it. You have to see it by effect.
It's
hard.
It's surprisingly difficult measurement to make. Anyway, so you've looked at these aurorae and you watched their behaviors, and you inferred that there was probably some water under there. And Scott has it up now. So here is the magnetosphere of Ganymede. This looks. Why don't you describe this for us a little bit?
This is the magnetic field lines around Ganymede. Here you can see the structure of Ganymede. Like the three outer layers are all water, like frozen water, then liquid water, like which we inferred, and then comes another layer of water. Then comes the rocky crust, and inside the red one, that's the iron core. And there the magnetic field is generated.
And that's critical, right? Because I mean, for example, Mars doesn't have a magnetic field because it doesn't have its dynamo, as it's called, it doesn't have one now, and so this molten core is pretty critical to even having a magnetic field at all. Correct?
Yeah, exactly. And it's important to stress that Ganymede is the only moon that we know that has its own magnetic field.
Now, I'll get to the other parts of the moon that you have outlined here in just a minute, but I want to go into this a little bit more. This magnetic field core, this core of the moon, the molten core, is that influenced by Jupiter at all, or is it just a relatively young body? I mean, why is it so? This tells me that it's a pretty active moon, right?
Yeah, it's a pretty active moon. It's a strongly differentiated moon. It's one of the most strongly differentiated planetary body that we know.
What's that mean?
Like that, it has these layers. And
okay.
It's very strongly layered and very heavy material inside and very light material on the outside, and it's clear in different layers. That's what it means with differentiated.
Okay, so my next question. So let me get some of the other guys involved in this. Daryl, can you describe a little bit what your role was in the project? I didn't get a chance to ask you before you joined, so give us an idea of what you were doing who you are and what you're doing on the project.
My specialty is planetary atmospheres, and I basically calculate how these charged particles interact with the molecular oxygen gas, and what radiation is produced from this interaction.
The oxygen interaction where? Does Ganymede have an atmosphere?
A very small atmosphere, probably column.
I didn't know that either. That's awesome.
Well, if it didn't, you wouldn't be seeing auroral activity.
I guess that's true, isn't it?
Right. You need a gas. And so we think the gas is maybe got a column density that if you took a square centimeter, you would line up in that column approximately a few times 10 to the 14 oxygen molecules above that square centimeter.
So you're telling me it's pretty
thin.
It's pretty thin.
Yeah.
Okay.
So tell us on the other atmospheres what that number would be.
Well, on the Earth, the column density of all the gas from the surface would be on the order of approaching 10 to the 26 molecules.
Okay, so that's 10 with 26 zeros, and the other is 10 with 14 zeros.
Right.
So it's a lot. And gobs and
big
gobs
difference.
more.
Or another moon, the second largest moon in our solar system, is Titan. And Titan has approximately the same column density of molecules as the Earth.
Wow.
So you have a contrast, the largest satellite with a puny atmosphere, and then Titan, the next largest, with something comparable to the Earth. Surface pressure, 50% larger than the Earth. In terms of density, about 4 times that of the Earth and at the surface.
So these inferred observation, or these inferred, the inferences that you're making from these aurora, at least I want to know, how do you know it was water that did that? Because at least with dark matter, they're not claiming to know what it is. They just know something must be there that's affecting the light from whatever it is behind it. You're saying pretty specifically that not only is this water, but this is liquid water. How do you know it's that and not something else?
Yeah.
Joachim?
We know that it's water because gravity measurements by the Galileo orbiter suggest that the first 1,000 kilometers of Ganymede has a mass density of 1, and in a cosmochemical context that can be only water, like that has this mass density of 1 gram per cubic centimeter. So we know it's water, that the outer layers, but one of the properties of water, which is vastly different if it's liquid or solid, is its electrical conductivity. That's by many orders of magnitude different if you have salty water or if you have frozen water.
Ah, good. I'm glad you brought that up, because my next question was, how do you know it's so salty? And you're saying it's because of the electrical conductivity of the...
yeah, exactly. That's what we basically measure with Hubble. It's that there is an electrically conductive layer that shields Jupiter's magnetic field and stops or reduces the aurora to move. And so
okay.
it's an electrically conductive layer, but we know its mass density is 1 gram per cubic centimeter, so it cannot be metal or something. And the only thing that comes to mind is water, and frozen water cannot do it.
So it's not that the moon, the Ganymede, has aurora. It's the movement of that aurora that really tells you what you're looking at, right?
That's right.
Okay, so Kurt, let me get you in on this. Describe for that how that's even possible with the Hubble Space Telescope. The observations that you made, tell us a little bit what you did and how you did it.
Okay, well, there's an instrument on Hubble called STIS, the Space Telescope Imaging Spectrograph, and it's really good at breaking up light into its constituent wavelengths and also forming an image at the same time through a slit. And we've used this instrument before to look at Io, Europa, and also Callisto, and we know that at these UV wavelengths, there are a lot of diagnostic features where atoms and molecules give off a particular fingerprint of emission or absorption that we can use the Hubble to identify. And what we saw are atomic emissions at 2 different wavelengths that are really diagnostic of a O2 molecule breaking apart as an electron hits it. And so that's the basic of our observing technique with Hubble.
So you measured it with STIS, got an image and a spectrum, were able to determine what the molecules were, and then the image itself, you were just able to measure where the aurora was and see where it went, right? And
exactly.
And spatially. Okay.
First did this in 2000. We got our first glimpse using the STIS instrument this way.
Lorenz, was this a surprise for you? I mean, was it, what did you think of all this when you started getting the data in?
It was not a surprise. There have been similar observations before where the auroral ovals have been seen the first time, and on we knew kind of Ganymede has these ovals compared to other moons that don't have ovals but other auroral morphologies. And so we really, this time with these new observations taken in 2010 and 11, we really aimed to look at a specific point in orbit of Ganymede to see the ovals best, and we observed over a longer period to exactly see what's going on with time with these ovals. So
give us a sense of how long that time was. How many orbits of Hubble did you get?
It was 2 times 5 orbits, so we observed like 2 times over 7 hours, and this has to be compared always in this case to the rotation period of Jupiter that governs the whole movement of the ovals, and this is 10 hours. So 2 times half the rotation period of Jupiter was enough to kind of resolve the spatial variability with time here.
So did you have models to start with that would describe what this would be like if it was saltwater, or did you go after the fact and sort of try and match up the observations with some models?
So I guess that's a question for Joachim.
Oh, okay. I didn't.
He brought up the idea, and
yeah.
I mean.
Well, okay. Let me ask it a different way. Before you answer that, Joachim, how did you even think of this idea? I mean, this seems to me like a pretty innovative technique for figuring out what the properties of a moon is like. Had this been done before? Is this something that you invented, or?
Yeah, I think this in that way, looking into a planetary body using the aurora, that's the first time that this technique is applied, and so I was brainstorming a while, like how you could use HST in another way. Now it's for 20 years around, and so and it always puzzled us because we're working in other ways on trying to understand if these moons have like internal water layers, and then it was just brainstorming for quite some time, and then suddenly it was there, the idea.
Okay, and so going back to what I mentioned earlier, when you saw, did you already have, since you had this idea, did you construct some kind of models first of what it must look like with salt water and then compare it with the observations, or was it the other way around?
Yeah. Then we started, like, when the idea was there, I was looking, like, with the student, like, who's the second author, like, with very simple models, just like with the dipole model of Ganymede's internal magnetic field and a constant magnetic field from Jupiter at the location of Ganymede, and looked like how then it would move. And then we saw there is a measurable difference, and then we just with time we made the models more and more complicated. And in the end, we were having a really complicated three-dimensional magnetohydrodynamic model, which we had to run on supercomputers, where the atmosphere and the ocean and with and everything full-fledged is included. So so the project lasted nearly 5 years until it now came to a close with the publication. And in that, we also figured that we really needed sophisticated models to rule out that other effects could modify the aurora, because it's indirect, like you say, and so you need to rule out as good as you can that other effects play in the role.
It can't be something else because of X, or it can't be that because of Y, and so that's good. I'm glad you did that. So Scott is currently showing us a schematic of the interaction between, and Kelly, if you could click on his thumbnail, the interaction between Ganymede and Jupiter. Do you have any you want to comment on this, Joachim? And then I have a question for Daryl after that.
Yeah, here you see Ganymede. Ganymede has its own magnetic field that's not included in the picture, but you very clearly can see the influence of Jupiter. The yellow line is Jupiter's magnetic field lines of Jupiter's, and they penetrate Ganymede. So they probe the ocean, and the magnetic field of Ganymede is of Jupiter is like a lighthouse. It's tilted, and when Jupiter rotates with 10 hours, also that lighthouse effect of the magnetic field is experienced by Ganymede, and then you have this electromagnetic effect that a time-varying magnetic field in something that's electrically conducting generates secondary magnetic field, which are opposed to the primary field, and sort of shuts the primary field off. And so the ocean of Ganymede shuts off the time variable component of this yellow line, which you can see in the image.
Wow, so I don't know how you keep all that straight. You've got one Jupiter's magnetic field has got to be pretty strong compared to Ganymede's, right?
Yeah, that's like around 100 nanotesla, and Ganymede's magnetic field is 750 nanotesla at the poles.
Wow, so so you've got to remove the effect of Jupiter's effects to see what is going on with, or do you just use what Jupiter's got to contribute to what you're seeing?
Yeah, exactly. We included all in the model, and then Jupiter's magnetic field, Ganymede's magnetic field, the effect of the ocean, the effect of the atmosphere, the effect of the magnetosphere of Jupiter, in the most complicated model that we had, and then put it into a supercomputer and just let it go. And
yeah, that's crazy. I mean, you got currents, magnetic fields generating currents, and I don't know how that makes my head hurt. But so Daryl, I have a question I'd like to ask you. This is in the Q&A app. This one's from Yuval Kogman. He's asking, and this has to do when you were talking about both Ganymede and Titan. How are Ganymede's and Titan's atmospheres so different? And not just their atmosphere, but their composition in general. Are their histories very different? And he says in parentheses, I'm a little surprised that they are so close in mass, but so different otherwise. So how are they, why are they so different, do you think?
Well, Titan has a nitrogen atmosphere, like the Earth's in terms of total density and so forth. It basically has a more benign environment as far as a magnetosphere. It's right at the fringe of Saturn's magnetosphere, whereas Ganymede is embedded in the magnetosphere of Jupiter. It has a very harsh environment, and so if you tried to recreate an atmosphere on Ganymede by evaporating water ice, one would, in this harsh environment that Ganymede exists, start stripping the atmosphere off by ionizing the molecules, the atoms, and then Jupiter's magnetic field would sweep by and pick these ions up. So that's one reason that there's a significant difference. If you calculate escape rates on Ganymede, they're very fast. They're very slow, relatively speaking.
Escape rates of what?
Of molecules or atoms. In other words, loss in the atmosphere, atmospheric loss rate. It would take To remove the nitrogen atmosphere from Titan at its present rate would take a couple of ages of the solar system. So obviously it's not happening. Whereas, you know, starting with what we've got on Ganymede, it's hard to conceive of how you could build it up before you stripped it away. I mean, to give you an illustration for something where I have a number, take Io and Europa. Their atmospheres have a resonance time of about 2 days. So if you shut down a mechanism for resupplying the atmosphere, in 2 days, you basically it would go away by atmospheric loss.
Okay, so well, you said the environment of Ganymede is harsh. What's harsh about it besides the is it magnetic field and also tidal forces? What else is
the charged particle environment, the energetic ions and electrons. So basically, if the thermal ions sweep by, where there are open field lines, they can basically interact. There's probably even acceleration of particles in the auroral area, whether it's where the open and closed field lines are. You could have electric fields along the field lines that could accelerate particles.
Okay.
So.
No, thank you, Yuval. That was a good question. I appreciate that. And so this one, I think I'll give. There's one more question here. I'm going to ask you this one, Lorenz. This is from Mehmet Khan. Are there any research spacecraft and satellites currently around Jupiter?
Unfortunately, currently there's no spacecraft around Jupiter. So we had the Galileo spacecraft in the 90s and the early 2000 years, but a new spacecraft is arriving very soon. That's Juno.
That's right.
So
when's it scheduled to arrive? Do you know?
July next year.
Okay.
Is the orbit insertion, I think, and then at the end of next year it will start doing science.
Okay.
But the Juno spacecraft is the mission is about Jupiter's atmosphere and magnetic field in the first place, and not really about the moons of Jupiter. So there will be not many opportunities to do a lot about Ganymede, for example, just because the orbit of the Juno spacecraft around Jupiter will not allow to do Ganymede science.
Okay. All right, thank you, Mehmet. That's a good question, and we look forward to seeing Juno get up there. So I want to go back a little bit to the composition of Ganymede. Scott, would you mind, or no, the aurora themselves? Could you put up the actual observations that they were taking? It was one of the ones that shows the aurora. And while you're doing that, I want to bring up the some of the characteristics of these oceans. Who wants to comment on like how thick the ocean, how thick the water layer is? Is it very accessible? Is it, if you were on the surface drilling down, how long will it take you to get to? Here, he's got it up now. So these, we never really talked about the observations themselves. So there's the moon of Ganymede here. You can see these blue streaks here. Kurt, can you describe for us what we're looking at a little bit, since you're familiar with the observations themselves?
Sure. So we're looking at Ganymede's leading hemisphere. So Ganymede's basically coming towards us in this field of view as it goes around Jupiter. And what you see drawn with those two pink lines is basically what we call the auroral oval. So there's one at the North Pole and one at the South Pole. And the idea that Joachim had is that with Jupiter's rotating magnetic field moving around, we'd see this pink oval slightly rocking by about 6 degrees or so. And so we could use these observations that you see in blue, tracing that line very closely, that we could test for this expected rocking and measure that accurately with these kinds of data.
So as those blue blobs move around in a certain way, that indicates what the magnetic field that they're interacting with is doing, and you can kind of see the rocking that you would predict.
Right, and those lines and those ovals, they're really close to where Ganymede's magnetic field intersects with Jupiter's magnetic field and combines in a way that lets plasmas from Jupiter's magnetosphere on into Ganymede itself along those field lines.
I was gonna ask about that, because in many other of both the Earth and also in some of the, like Jupiter and Saturn, you see the aurora very close to the pole. And so here, as you just said, but maybe you want to explain it a little further, is that it's more complex because it's not just Ganymede's field and it's not just Jupiter's field, and so that makes the aurora belt actually a belt further down than a cap, right?
Right, right. And in this view, it's at a little bit lower latitudes than the poles, even though it's sort of drawing a circle around the pole itself, just because of the way the plasma sort of buffets and pushes into Ganymede's magnetosphere. We're looking at the plasma is flowing towards us faster than Ganymede is, if you will. And so there's a way that the magnetic field lines are all bent and twisted in a way that lowers this region where these lines connect to lower latitudes in the particular view we have. When we look at the opposite view, these ovals are higher up as a result of this interesting physics of how these two merge together and interact.
So what do we look? I always ask this question when I'm looking at images. What wavelengths are we looking at here, and does that matter?
So we're looking at 135.6 nanometers of light, and this is a real diagnostic emission line from atomic oxygen. And we've seen this at Io, Europa, and Callisto now even, in addition to Ganymede here. And this is a nice clean image with the Hubble instrument that we use. And as we explained before, this is a diagnostic for electrons busting up molecular oxygen atoms into two different atoms, and both of these emit light at different wavelengths.
Okay. Well, so Wout van der Heide, hello again. Good to see you back. He's asking on the Q&A app, what caused the groove surface of Ganymede? Who wants to comment on that? I'll leave that to any one of you. Joachim?
Well, that's not really my area of expertise.
Okay.
But the so what you sometimes hear is that's the feature that goes back to 2 or 3 billion years, and there is even speculation that there's been flooding on the surface, like by liquid water then, and so that would generate like these structures on the surface of Ganymede.
Okay, Scott, can you put that schematic of the interior of Ganymede back up? I want to talk about that for a minute. So here is all the different parts of Ganymede. You've got it covering an ice crust, a saline ocean. How do you know? First of all, why don't you talk about how big each of these layers are and how far down they go? Joachim, I guess.
That is mostly known from gravity measurements by the Galileo orbiter. The Galileo spacecraft flew by 6 times close at Ganymede and it could measure the gravity field around Ganymede, and from that you can infer like the internal structure.
So we've got a layer of liquid saline ocean, and then right underneath that, or I'm sorry, what am I looking at? Yeah, right underneath that is an ice mantle. How come the ice is below the liquid? You would think it'd be the other way around. He said that's what my intuition would tell me.
At Europa, that's the case. You have an ice crust and then an ocean, and it comes to rock. Here at Ganymede, the outer water part is much more massive, and ice and water is a very complicated molecule. In its frozen phase, it can have more than 10 different phases. And under higher pressure, like frozen water assumes a different phase, and that's the icy mantle. And so that's why it's possible. Yeah. So that's why it's possible that you have different phases of ice. The ice crust is the normal ice that we know.
Right, that makes sense. I understand that part, why it's there. But I was confused as you had liquid and then followed by more ice, and that's what. And you're saying it's because of the pressure.
Yeah.
Okay. How far down is that saline ocean from the ice crust? In other words, how thick is the ice crust?
That's unknown. Like in our model, that fits well with the data. Like the ice crust is 150 kilometers, but it could be smaller. But the only thing that we really can infer from the data is that the ocean cannot be deeper than 330 kilometers, because then it wouldn't be consistent with the observation anymore. Then it would influence the aurora in a different way. So we can set hard constraints on the total depth of the ocean, that it needs to be like within the first 300 kilometers.
Man, it just blows me away that from wiggles of charged particles you can get so much information. That's amazing to me.
So I actually have a question, and I just wanted to say to the team, I saw the preprint of this paper a while ago, and I was really excited about it. I was like, this is awesome. I can't wait to hear about this. Anyway, I'm not a planetary scientist at all, but I just think this is amazing. I wanted to ask maybe Lorenz or anybody who wants to answer this question, because you all are not only working on Ganymede, and I know we've had you on Hangouts before, and we've talked about Europa water. So I'd like somebody to say, okay, so we have this Ganymede, we're learning about Ganymede, that's really cool, we're learning about Jupiter, and we're learning that Jupiter, the electrical and magnetic field around Jupiter is no picnic, but in general, tell us in the landscape of the quest for water, where does this fit in all of our thinking about where is water and searching for life and all that kind of stuff?
The new thing about it, I mean, there have been these suggestions that there is water on Ganymede before, and people easily take this as granted just because they want to have water basically everywhere possible. So whenever you have just the slight idea that somewhere could be water, people will rather believe it than not. And so the advantage now is that we really have a much better evidence that there is water, because there's basically only this one explanation to explain the Hubble observations. And this is, of course, I mean, water is this one of the three basic conditions we can think of that life needs. And now we have a place where we know water is. And similar, I mean, we think that there's a ocean inside Callisto, the outermost moon, but we only, so to say, have the observations from the Galileo spacecraft, which give like really suggestions that there's an ocean too. But I think this is like a really good proof with Hubble that there is liquid water. And
so it seems to me, being older than 25, that in the old days,
no, I don't believe it.
I mean, we didn't used to think about water being all these different places in the solar system. So to me, it's kind of meaning, wow, we could find, when we start thinking about exoplanets and next generation telescopes and looking into the, next 30 years, which I probably won't be here for, but young astronomers will be, finding water reservoirs in all kinds of environments that before we didn't think. And this thing about water on moons really intrigues me. I mean, it's, it's quite interesting.
I'm totally with you on that. I mean, I remember when water ice used to be the big news, and now we're finding liquid water. I mean, it's going even far beyond what we were excited about before. Like okay, water ice, awesome, that's so intriguing, and now we're seeing liquid water.
Like oceans.
Yeah, like
significant oceans.
But you do you do need more like information than only like the Hubble images in this case, because before we knew that in this case the outermost layer is either liquid water or ice. We knew it from gravity measurements, like Joachim said. So and then we can say like if this ice or water layer, so we know already it's ice or water, is electrically conductive, then it must be water. But without this additional information, it could be another conductive material, and we can only see conductivity, like Joachim said, and not water with this technique. Right. But still, I mean, it's great. But you do need additional constraints for this from other measurements.
Absolutely. But you're young. See, you knew there was water on Ganymede. When I was, a young astronomer, we didn't know there was water on Ganymede. So.
But I think Galileo was just getting around to letting observing the moons, right, Carol? Okay. So I want to talk. Well, go ahead.
There's also a more global answer to that question. Is you got to remember that hydrogen is the most abundant element, and oxygen is the third most abundant.
Yes.
And when you get into the outer solar system, we know that that's past the ice line. And so when our solar system was formed, you could capture a lot of water in the form of ices out there. And I think one should probably be thinking in the future of why some moons don't have oceans, as opposed to be surprised they do.
That's a nice way of putting it, yeah.
If you take Titan, for example, from the tidal love number that has been determined by Cassini flybys, we're almost sure the evidence points that there's an ocean beneath Titan's surface. We also know from tidal or measurements of the tidal numbers associated with Enceladus, there is either an ocean just below the South Pole, or maybe it's also global as well, with more, for some reason, in the beneath the South Pole where we see these jets. So I think, you know, we should not normally have an ocean with a moon, but think when you're in the outer solar system, why not?
That's an interesting idea.
Nice,
Okay.
that's
So
nice.
Daryl,
because I mean, it's all like Daryl said. They all, most of the moons have a frozen water layer outside, and they all have energy sources inside. And so it's like any lake in the wintertime. It freezes outside because it's cold, but the earth underneath is still warm, and then so there's really good chances that it melted from the inside, and you have the blanket of ice that shields the water from cooling out.
So Daryl, I want to extend this a little bit to thinking about the other Jovian moons. We talked about Lorenz mentioned Callisto. Do these other moons have atmospheres that might have aurorae that we might be able to observe?
Well, we just have had a paper accepted with Icarus for Callisto, where we finally, with Hubble, have detected evidence for an oxygen atmosphere. This atmosphere is about somewhere, let's say, 50 times higher column density than the one on Ganymede, and also the one on Europa, you know, in terms of.
Is it possible to use this technique to maybe see if there's water there?
The problem basically is the emissions are so weak that right now, as we had to go from the STIS instrument that was mentioned before to study Ganymede, where the upper limit on, and you know, in these units called Rayleighs is 15 of detectability. We had to go to the COS instrument on Hubble, where we could get down and detect at the 2 or 3 Rayleigh limit. So, and what we had to give up in return was spatial information.
Right, because the COS doesn't have an imager. So
right, so that was the trade space, but we finally had to go that route to actually detect it. I mean, we've tried it back about 15 years ago with STIS, and only got an upper limit.
So I'm not really familiar with all the instruments on Juno, but is there a chance with that when it gets there to improve some of these observations, or is it going to be doing something else entirely?
I can talk about that.
Okay, go ahead.
There is a UV spectrograph on Juno, run from Southwest Research here, and the thing about Juno though is that it's a spinning spacecraft, and so it only gets like a quick glimpse of the satellites at any one time, and it can't stare at a target like Hubble can, for example, and build up good signal-to-noise ratio.
I see.
There are just only a few occasions where we'll be able to try to get some of these images, and they won't quite be as sharp as Hubble in terms of resolution, but we'll see what we get.
Okay. Well, hopefully. Go ahead.
I was going to make another comment just to say how great Hubble is the Galileo spacecraft had a UV instrument on it, and it used to fly by Europa and Ganymede, you know, a couple hundred kilometers above the surface. It was never able to detect the oxygen lines that we use and detect with Hubble to do this research.
Was that because the detectors they just weren't sensitive enough?
Well,
Galileo?
With telescopes, you need collecting power.
Okay.
The telescope mirror. And, of course, with Galileo spacecraft, the proposals were due before Voyager got there, and the technology was probably in the early 70s at the latest. And you know how detector capability has advanced through the years.
I know. In some ways, Hubble is cheating because it gets to be rebuilt. These other spacecraft can't get. They don't enjoy that capability.
Well, that's why we love it.
That's right. That's why we make videos about it.
But let's think that life is cheated by evolving. I mean, come on.
Well, we're comparing. It is cheating. We're comparing apples and oranges here. We can't compare Galileo, which had to be planned in 1970, whatever, against an instrument that can be repaired over 25 years. Adam Synergy is asking on the Q&A app. This is a good question.
Really good question.
Does all that water create any measurable obliquity, or libration in Ganymede or any of the other Galilean moons? I'm going to have to look those words up.
You don't know what libration is?
No.
So libration is like the wobble as it's spinning.
Oh, good. I didn't know that. And obliquity.
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 Do we need to learn you some English?
I need me some learning.
I
need some learning. I never use those words.
I can give the answer if you're interested.
Yes.
No, we just want to say the words. We just want to say the words over again. Yes, please answer the question.
Yeah. That would actually be very diagnostic for the existence of the ocean, and some people try to study that with different telescopes, with radar telescopes, to look at like how the liberation, like how these moons change, like when they go around Jupiter. So that's in progress. I know a couple of people who work on that, but it's not been measured.
Thanks, Adam, for pointing out the limits to my vocabulary. Yes,
but you ask about the aurora on other moons, and Lawrence he's an expert on the aurora of Io and Europa, so I just wanted to point that out.
What was the question on the aurora of the other moons, or?
Yeah, if they have aurora, if Io or Europa has aurora.
I was asking that to Daryl earlier, so.
Yeah. Oh, okay, we had this early on. They all do have aurora, and especially we talked about Callisto, but especially these oxygen lines. We do see these oxygen lines at all moons, and in the case of Europa, it's very similar. It's also O2 mostly, and in the case of Io, Io is the volcanic moon that the volcanoes spit out sulfur dioxide and sulfuric material all the time. We have a sulfur dioxide atmosphere, but it also contains oxygen, so we also see these oxygen lines. And interestingly, it looks very different at all moons. So we do not have ovals. Joachim mentioned this before, because only Ganymede has this intrinsic magnetic field, and the shape of the emissions at the other moons is very different. So sometimes we have bright spots at the equator. At Europa, it's kind of unknown what exactly is going on. But only at Ganymede we have ovals at a moon, at least.
Okay, good. Now I have a question here from YouTube. This is from aurorae1234. It may have been answered already, but can you estimate the salinity? And how does the salinity of this water compare to our oceans?
The salinity that we find fits the data very well is 5 grams of salt per 1 liter of water, and at Ganymede, it's assumed to be magnesium sulfide as the main salt in the ocean, and this is the second most salt in the Earth ocean. There is sodium chloride is the most abundant salt in the Earth ocean, and the Earth ocean have a salinity of roughly 35 grams of salt per 1 liter water. So the salinity is
much less.
It's a little bit less, like a factor of 7 or so.
Good question, and I even understood the words you used. Jukio is asking, my question is, where did the water come from? I'm starting to have doubts that on comets bringing it, and this alludes to what you were talking about, Daryl. Do you want to comment a little more on that, or do you just want to leave it where you had it?
Just to reinforce the answer, that basically out at Jupiter's distance and beyond, it's when the solar system was being formed, the temperatures of the planetary protonebula was sufficiently cold that water took the form of ice out there, and that allowed one to accumulate a lot of mass building material to make these objects.
Okay, good question. Okay, so Scott, am I missing anybody? I got YouTube and Q&A. You got any Twitter stuffs?
There's been a lot of Twitter activity, so thank you, especially Pilonaut. Heather, you are fantastic of getting that out there. I had actually a few questions that we answered while on air, so I'm not going to repeat them, but they were really good questions that you guys were just on the ball on getting the answers for. But let me see here if there's anything else. Yeah, one again was asking about the salinity of the ocean that you just answered. But again, honestly, I just want to thank all of our followers and those that are on the Hubble Hangout hashtag for all the engagement. You guys have been fantastic.
Yes, thank you.
And yeah, there's just been so much of it. So you guys are awesome.
Well, in all of my obliquity, I am going to get some libration.
Wait.
Wait. That's
Wait.
Yes.
Wait. I have another question.
Okay.
So we know that when we looked with Hubble at the Jupiter aurora, we could see a trace of the presence of Io because we have this picture of the interaction and the influence because there's this little button or whatever that disturbs the aurora. Do we see evidence? I mean, if you pick apart the aurora on Jupiter, can you see the evidence of the interaction with Ganymede?
Yeah, Ganymede has its own sort of footprint, and Hubble's been doing a great job measuring the footprints. It seems to vary on short time scales, and it speaks to a connection with the magnetospheric variability within Ganymede, driving some sort of variability that you see in the spot on Jupiter. And, we'd really love to get some simultaneous measurements, maybe with Hubble.
Yeah.
And with the JUICE mission in 2030,
wow.
watching those vary at the exact same time.
Definitely puts me out of the Hubble generation.
That's great. Thank you, Kurt.
Yeah.
We need a second Hubble to look at both Jupiter and
Yeah.
the same
That's
time.
true.
I'm down with the second Hubble.
Yeah. Well, I think we're calling it W first for now, but that's not quite the same. I know it's a wider field, but still. Quick question from Yuval Cogman again, and how does? And then we're going to have to sign off very quickly. How does the salinity, pressure, temperature affect the phase? Does anybody know the answer? I'm not quite sure what you mean by phase in this context. Anybody understand?
You mean the lag in responding to the induced field?
Yeah, maybe.
You know, I think like he means like there's a phase diagram like a temperature and pressure if it's liquid, solid, or gaseous, and if you put salt in it, I mean that's crazy complicated with water. So it's so we could like get out a chart and we have a lesson on that like for a couple of hours. So it strongly affects it, but it's
yeah. That's a topic for another show. We'll just
Yeah, absolutely. Yeah. That's great.
All right, folks, guys, I want to
question.
thank you all for watching. This is exciting work. We look forward to hearing more from you guys as you learn more. Joachim, Daryl, Kurt, and Lorenz, thank you all for showing up and sharing us this information. I want to thank you all. Thank you all for watching. We're going to stop it here. Don't forget to vote on the Ode to Hubble, also Hubble Mania. Follow us on Twitter at Hubble Telescope. Also, subscribe to us at YouTube at the Hubble Site channel. So until next week, where we will be talking about, I forgot to have that in front of me. We will be talking about the, we will be talking about space.
Hubble Source Catalog.
Hubble Source Catalog is being released.
How do you find out all the brightness of all the objects that Hubble has ever observed? How's that?
Right. So until then, on behalf of everybody in this hangout, I want to thank you all for watching, and as always, keep
looking up. Thank you very much.
All right.
So with that in mind, Hubblers and Hubble huggers, you love the Hubble Space Telescope, and if you love it enough, you may have felt compelled to make a video and to enter it in a contest to win some really cool prizes. So if you do plan to enter, today's it. This is your last chance. It ends midnight Central European time, which is about 7 p.m. our time, Eastern time. So you don't have it's just hours left to submit. So please go ahead and do it. And then what happens, and the link to that is in the description box also below. But what happens next is a segment that I'm going to let Georgia Bladen talk about. She's the Hubble manager, the social media person at the European Space Agency, and she has joined us to talk a little more about what's next for the Hubble, the Ode to Hubble video contest. Georgia?
Thanks, Tony. So first of all, a huge thank you to everyone who has sent in their videos. I've had a little sneak peek at the ones we've had so far, and there's some great stuff in there. So, as Tony said, you've got till midnight Central European time tonight to get your entries in if you haven't already. When we've got all of those entries in, at 2 p.m. Central European tomorrow, which I think is 9 a.m. Eastern, you will have the opportunity to crowd vote the entries to get us down to a short list of 6 for each of the 2 categories.
So the URL that you currently have for submitting will change into something else.
Yes, you will see if you go to that page, there'll be 2 links that appear magically tomorrow that you can follow to go and vote for your entries, and the current submission links will take you.
There you go. Okay.
There we are. When you get to this page, this is where you will be able to vote. So you'll have to sign into Facebook. It will take you to a page like this, and all of the videos for that category will then be displayed. Got a sneak peek here. You can play them, you can visit them on YouTube, and to vote, you like them as you would on Facebook. And the 6 for each category that get the most likes will then be sent to our judging panel.
Can you only like
2 winners?
Can you only like one?
No, you can like as many as you like. So if you watch something and you don't like it, don't like it. And if you do like it, then you can like all the ones that you think deserve to be in the shortlist.
All right. So if you don't have a Facebook account, you guys need to get one of those too, because we're going to need you to vote. So, and then the ones that have the most likes. How long will this be going on, Georgia? Oh, it says right there, 1st of April, 2015.
It does indeed. So it'll be until the 1st of April, and then it will go to our panel of judges, and they will select 2 final winners, 1 from each category. And those final winners will be announced at the anniversary on the 24th of April.
Wonderful. And what do they win? This is my favorite part.
What is a great prize, I think. I would say that.
Me too.
It's a piece of mounted solar array, ESA made, that was on Hubble. So
an actual piece of an actual solar array that was actually on Hubble.
Actually on Hubble.
Yeah, you actually get your own little bit of Hubble.
Actually.
Actually Hubble.
Yes, well, that's important.
It is. And you also actually get a mounted image of the 25th anniversary image.
Okay, so this comments. So Scott, why don't you tell everybody how they might be able to do that?
Absolutely. So the easiest way for us to see your questions and comments is to use the Q&A app, which is here on both YouTube and Google+. So whether you're watching it embedded somewhere on another website or on Google+ watching us there, on the very bottom, it will allow you to pop open and ask us a question. I'm already seeing one coming through from W. Vanderheide, and telling us good evening, Hubblers. So that is a great way for us to interact with you. We can actually select your questions and answer them on air, and it puts a timestamp onto when we answer it. You can leave us questions and comments just in the regular YouTube comment area, and also over on Twitter. We are, or I am more, looking over at the hashtag Hubble Hangout, to where we will not only be monitoring questions, but I will be live tweeting and putting out some of the images that we're discussing today during the show. So please feel free to get a hold of us in all those different ways. And as Tony said, subscribe and follow us on Twitter so we can have more of a conversation during and after the show.
Good. Thank you very much, Scott. So we're doing that now. We're Hubblers now, not Hubble Huggers.
I enjoy Hubblers much.
Is that a contraction?
I like Hubblers more than Hubble Hugger. You know me.
Yeah, I don't know. I kind of like Hubble Hugger. But all right, well, take a vote. Tell us what you think. If you want Hubblers, then that's what you are. If you consider yourself a Hubble Hugger, say that too. And I want to know, because I kind of like Hubble Hugger better. Okay,
I'll create a poll later on
yeah, good idea. Let's get social. Right. You're driving the internet, so that's a good idea. That's a good. Hello, everybody, and welcome to this week's Hubble Hangout. My name is Tony Darnell. I work at the Space Telescope Science Institute, and once again, we've got a great hangout planned for you. Turns out, and I didn't actually know this, but turns out there's water on Ganymede. So it is, and today we've got some observations from a Hubble Space Telescope that were announced earlier today. We've got the scientists on hand who took them to tell us what they found. But before we get started and get going in earnest with the hangout, let me just say a couple of things about Hubble 25 and some things I want to put on your radar. This weekend, we're going to be at South by Southwest. NASA will be at South by Southwest doing all kinds of fun activities. And so if you're in the Austin area, please stop by the booth at the interactive exhibit and there'll be some panels going on there as well, one on Sunday and another one on Tuesday, the following. So if you follow us on Twitter, and if you aren't, you should be, at Hubble Telescope. You will find out all about that as the weekend progresses. Also, if you're not subscribed to our YouTube channel, which is Hubble Site Channel on YouTube, you need to get that way, because we got all kinds of fun things going on that channel as well as Hubble 25th goes on. Also, Hubble Mania is still happening. So if you go to hubble25th.org/go/Hubble-mania, you can vote for your favorite Hubble images, and the link to all that is down in the description box below. Also going on and ending today is the Ode to Hubble video contest, which we're going to talk about a little bit more in just a minute. But first, we want your questions and your
to the voting pages. Yes, I have a little preview that I can show you on what it will look like.
This is what you can expect.
So, when I've got my head around doing this.
Okay. So, so the same URL will be valid tomorrow. You go there, instead of being able to submit, you'll be able to do some voting. While she's getting that up, I'll just tell you they've really got some great things. They've got two categories. One of them is for people 25 and under. You're the Hubble generation. And then there's another category for people who are over 25, which I just barely missed the window. I used to be I was almost there where I could have been the Hubble generation, but I just missed it.
Yeah, a couple decades, man.
Yeah, sure, Tony. Just by many years.
Yeah. Well, I'm a Hubble old generation, I guess. Okay, go ahead, Georgia. We see your screen.
You're more of an Edwin Hubble generation.
Edwin Hubble. Oh, where's my ball?
Oh, mean.
Harsh. That's really harsh. So this is the page that you will need to go to, that you've got a link to. So this is where the links will appear tomorrow. These links up here, which are currently to submit, you will then be able to use in order to vote. And when you do come to vote, can you see this page?
Yes.
Yeah.
We still see the Ode to Hubble page.
We see the main Ode to Hubble page.
If you've moved,
okay.
That's still what we're seeing.
Pause for suspense. This is my first time.